Hello students, in this session we are taking inspiration from the real power series and we are trying to define trigonometric functions. That is, to be speaking here, it will be Cos Z and Sine Z, and we are going to see how they are related to the exponential function we have just defined before. For that, first we are going to define Cos Z. Cos Z is equal to, it's defined as 1 minus Z square divided by 2 factorial plus Z raised to 4 by 4 factorial plus etc. plus the general term minus 1 raised to n into Z raised to 2n divided by 2n the whole factorial plus etc. So, this is equal to summation n is equal to 0 to infinity minus 1 raised to n divided by 2n the whole factorial into Z raised to 2n. Okay. First we defined Cos Z as a power series. Now we are going to check whether this Cos Z is having a radius of convergence. Radius of convergence of Cos Z. This is what we are going to check. By an earlier preposition, we said that suppose if we have the power series to be summation n is equal to 0 to infinity a n into z minus a the whole raised to n, if limit n tends to infinity modulus of a n divided by a n plus 1 is existing, then that will be equal to the radius of convergence of this power series. This was a preposition which we had earlier seen. So, we are going to use this preposition to find the radius of convergence of Cos Z. Okay. So, to be specific, here we are having summation n is equal to 0 to infinity a n into z minus a whole raised to n. Instead of that, we are having summation n is equal to 0 to infinity. We defined Cos Z to be minus 1 raised to n divided by 2n factorial into z raised to 2n, right? So, here we are having a n to be minus 1 raised to, instead of a n, we are having a little change, that will be a2n. a2n is equal to minus 1 raised to n divided by 2n the whole factorial, right? Okay. And also we are having, instead of a, we will have 0. So, now let us check whether the limit we said earlier is existing or not. Consider limit n tends to infinity modulus of a n by a n plus 1. By the kind of power series we are having here, the instead of nth term we are having the 2nth term, and the next term that is going to happen will be 2 into n plus 1th term. Okay, 2 into in the braces n plus 1. So, instead of this we can write limit n tends to infinity modulus of a 2n divided by a 2 into n plus 1. That is how we find the limits here, and that is equal to limit n tends to infinity modulus of minus 1 raised to n by 2n factorial divided by minus 1 raised to n plus 1 divided by 2 into n plus 1 the whole factorial modulus. And since the modulus is coming, we can clearly make this minus 1 the whole raised to n and minus 1 the whole raised to n plus 1 to be equal to 1, because modulus is happening. So, this can be rewritten as this is equal to limit n tends to infinity, the clearly the factorial signs those are those are all positive, so the modulus sign can be removed and this term is taken up. So you are going to get 2n plus 2 the whole factorial divided by 2n the whole factorial, which is equal to limit n tends to infinity 2n plus 2 into 2n plus 1, and you definitely have 2n factorial in the numerator and 2n factorial in the denominator. Both of them cancel out and we are going to get this, and this will definitely tend to infinity and the limit is existing. That will mean the radius of convergence of cos z is equal to infinity. So we are getting an important property of cos z, that radius of convergence of cos z, which we define now, is infinite, right? Okay, so also we can say that the power series of cos z is convergent in the entire complex plane. That is what entire complex plane, that is what that means. Fine. So now that we have defined cos z, we are instinctively going to define sin z. Sin z is equal to, we are inspired from the real power series, remember that. Sin z is equal to z minus z cube by 3 factorial. In the real power series, that will be, instead of z we have x, that's it, plus z raised to 5 by 5 factorial plus etc, plus the general term minus 1 raised to n into z raised to 2n plus 1 divided by 2n plus 1 the whole factorial plus etc. So that is equal to summation n is equal to 0 to infinity minus 1 raised to n divided by 2n plus 1 the whole factorial into z raised to 2n plus 1. This is the general term. So what we are going to do is the same thing. We are going to find the radius of convergence of sin z the same way. Limit n tends to infinity. So here let us just say that summation n is equal to 0 to infinity a n into z minus a the whole raised to n is the general term, that is equal to, here summation n is equal to 0 to infinity minus 1 the whole raised to n divided by 2n plus 1 the whole factorial into z raised to 2n plus 1, right. So that will mean that a 2n plus 1 is equal to minus 1 raised to n minus 1 raised to n divided by 2n plus 1 the whole factorial, and also here a is equal to 0. That is an observation. So here limit n tends to infinity modulus of a n by a n plus 1. So instead of that, here we are going to have limit n tends to infinity, the same. Here we will have a 2n plus 1 divided by a, instead of n you will have 2n plus 1 plus 1, that is it. And just apply and substitute. That is equal to limit n tends to infinity minus 1 the whole raised to n divided by 2n plus 1 the whole factorial, that is a 2n plus 1 divided by minus 1 raised to, instead of n I am going to have n plus 1 replaced, 2 into n plus 1 the whole factorial, the whole under the modulus, and the minus 1 the whole raised to n and minus 1 the whole raised to n plus 1 will vanish to be equal to 1 because of the modulus sign. Rest is factorial, that will be definitely positive. So, we are having limit n tends to infinity 2n, here 2n plus 2 plus 1. So, 2n plus 3 the whole factorial divided by 2n plus 1 the whole factorial, that is equal to limit n tends to infinity, we will have 2n plus 3 into 2n plus 2, and we are having 2n plus 1 factorial in the numerator divided by 2n plus 1 the whole factorial, those they cancel out, and this will definitely tend to infinity, the limit is existing. So, limit is existing will make us know that the radius of convergence is equal to infinity. So, we just found out that radius of convergence of sine Z is infinite, which is a very important property of sine Z. Okay, and from that we are going to get that the power series of sine Z is convergent in the entire complex plane. That is an important conclusion we are getting about sine Z and cos Z, and know that both of the power series sine Z, cos Z, both are convergent, and that will definitely mean that from preposition 2 point, please refer the preposition 2.5b, we will get that both the functions sine Z and cos Z are infinitely differentiable. In the entire complex plane. Note that this is true for the exponential function e raised to z also. Okay. So, we can get an important result from there, that e raised to z, sine Z, cos Z are entire functions. That means they are analytic in the entire complex plane. This is a very important result and an example of functions which are entire. Okay. Now, let us see the derivative of sine Z and cos Z. So, this is our next idea, derivatives of cos Z and sine Z. So, let us see how we can find it. Okay, we have cos z to be equal to 1 minus z square by 2 factorial plus z raised to 4 by 4 factorial plus etc. plus minus 1 the whole raised to n into z raised to 2n divided by 2n the whole factorial plus etc. And we said that that is generally equal to summation n is equal to 0 to infinity, the general term, minus 1 the whole raised to n divided by 2n the whole factorial into z raised to 2n. Okay. So, we noted earlier while finding the radius of convergence that the term sitting here is z raised to 2n. Instead of the general term n, we are having z raised to 2n. So, let us have a simple work done to make it in the same form as the power series. Okay. So, suppose I am going to say that this is equal to n is equal to 0 to infinity a n into z raised to n. Okay. Note that the z raised to 2n will mean that only the even powers of z will exist in the power series, right. So, we can write it as a n is equal to, okay, I am going to write a n itself and here I am having z n. Okay. So, if n is odd, definitely a n is 0. Okay. Now, if n is even, okay, look here it is even, right. So, when it is even, what was the power here? It was n. That means half of the power sitting here, right. So, this will be 2n by 2. So, if here the power is n, the power of minus 1 will be n by 2. So, I am writing minus 1 the whole raised to n by 2 divided by, here if it is 2n, here we have 2n factorial. When it is here n, in the denominator I am going to have n factorial. So, what we did is we made our cos z in the same form as that of the power series which we defined at first. Okay. Now, what are we going to do? We are going to find the derivative of cos z. So, note that we are again going to use preposition, we are going to use preposition 2.5b. This is a very important preposition, we are often using it. So, we are having the power series as like this. So, by preposition 2.5b, we know that this is equal to summation n is equal to, here the k in the preposition will be 1 because we are taking the first derivative. So, summation n is equal to k to infinity. Instead of k, I am having 1 to infinity. Here we will have n into a n into z raised to n minus 1. And let us see what is the coefficient. Here the coefficient will be n into a n and let us define it. So, here when we are defining, I will be getting minus 1 the whole raised to n by 2. I am multiplying this a n with an n. So, in the numerator I have an n, in the denominator I am having n factorial, the n and n cancel out and the remaining term in the denominator is n minus 1 factorial. If n is even, okay, here it will be 0 if n is odd. So, this is a general term. Okay. Now, we are going to expand this term. Now, when we are going to expand, we are going to get this to be equal to when n in 1 into a1, it is already calculated 1 into a1, when n is odd that will be 0. So the first term will be 0 into z raised to 0 plus next is 2 into a2. 2 into a2 will be n is even. So that will be minus 1 the whole raised to n is 2, right. So that will be 2 by 2, that will be 1 minus 1 divided by 2 minus 1 factorial, that will be minus 1 divided by 1 factorial into z raised to 2 minus 1, that is z raised to 1. Okay. The next will be 3 into a3, that will be 0 into z raised to 2. Okay. The next will be 4 into a4, the coefficient will be 4 into a4. 4 into a4 is already calculated when 4 is even. So 4 by 2 is 2 minus 1 the whole square will be 1, that will be 1 divided by 4 minus 1 factorial, that will be 3 factorial into z raised to 4 minus 1, that will be 3 plus 5 into not 5 4 in yes 5 into a5 will be 0. Okay, and that will continue. Okay. So now you got this to be equal to minus z plus z cube by 3 factorial minus etc. So if you are thinking about the next term, this will be, to be very precise, this will be a5 5 into a5, right. So the next will be 6 into a6. So 6 is even, we will be having 6 here. So 6 by 2 will be 3, minus 1 the whole cube will be minus 1. So here you will have minus 1 divided by 6 minus 1 factorial will be 5 factorial into z raised to 6 minus 1, that will be 5. Okay. That will be 6 into a6, then 7 into a7 will be 0 plus etc. So if you have one more term, you will be better understanding. So here you will have z raised to 5 divided by 5 factorial plus etc. Okay. And that is equal to, I am taking the minus sign out, that will be z minus z cube by 3 factorial plus z raised to 5 by 5 factorial minus etc. Okay. When we check it out, that is nothing but minus sine z, which we had defined earlier. So this is one important analogous property we are getting in complex analysis, which is nothing but d by dz of cos z is equal to minus sine z, and we know that this is obviously true in the real sense, and we just prove that it is true in the complex analysis about cos z. So now let us see how we can find the derivative of sine z. So we have sine z to be equal to z minus z cube by 3 factorial plus z raised to 5 by 5 factorial plus etc. plus the general term minus 1 the whole raised to n into z raised to 2n plus 1 divided by 2n plus 1 the whole factorial plus etc., which is equal to summation n is equal to 0 to infinity the general term minus 1 the whole raised to n divided by 2n plus 1 factorial into z raised to 2n plus 1. Okay, so we are changing it in the same form as that of the power series, that is equal to summation n is equal to 0 to infinity a n into z raised to n. I am saying like this, and note that 2n plus 1 will mean that is an odd number. So as we had done earlier, here we will say a n is equal to in two terms. Here the odd terms will be having the coefficients when n is odd. When n is odd, we know that, see, 2n plus 1 for the term z raised to 2n plus 1, I am having n here for minus 1's power. So how to relate both of them? 2n plus 1 minus 1 divided by 2, that will be n, right? So if I have a term here to be n, that term minus 1 divided by 2 will be the term here. So if n is the term here, minus 1 will be having the power n minus 1 by 2. Okay, and in the denominator the same power, that will be n factorial, and when n is even, we see that the coefficient is 0. Okay, now we are going to use the preposition 2.5b. Okay, the preposition says d by dz of the power series which has a radius of convergence, positive radius of convergence, is equal to summation n is equal to 0 to infinity n into a n into z raised to n minus 1, and z raised to n minus 1, and here I am going to talk about the our coefficient. The coefficient will be n into a minus n into a n, which is equal to, just see what is, n is odd here and n is even here, and in the case of even it's it's 0, and in odd we are multiplying it with n, so we will be having minus 1 the whole raised to n minus 1 by 2 divided by n minus 1 factorial. Okay, so now you are going to expand with this knowledge. Okay, this is equal to, when there is a little difference here, by preposition we have it to be 1, right? Our k is 1. So let n is equal to 1. So I am having n into 1 into a1. 1 into a1 will be, when n is 1, here it will be 0, minus 1 raised to 0, that will be 1, divided by 1 minus 1 factorial, that is 0 factorial is defined as 1, into z raised to 1 minus 1, that is 0, plus next will be 2 into a2, 2 is even, so that will be 0, plus 3 into a3, 3 is odd, so 3 minus 1 will be 2, 2 divided by 2 will be 1, minus 1 the whole raised to 1, that will give you minus 1 from the numerator divided by 3, 3 minus 1 factorial, that will be 2 factorial, okay, into, when n is 3, so here we will have z 3 minus 1, z raised to 3 minus 1 will be 2, plus the next will be 4, 4 into a4, 4 is even, so we will be having 0, plus 5 into a5, 5 into a5 will be minus 1 raised to 5 minus 1, 5 minus 1, 5 minus 1 will be 4, 4 divided by 2, 4 divided by 2 will be 2, minus 1 the whole square will be 1. So, you will have my 1 to be the numerator divided by 5 minus 1 will be 4 factorial into z raised to 5 minus 1, that will be 4, plus etc. So, this is happening like that, and that is equal to 1. The first term will be 1, the second term will be minus z square by 2 factorial, the next term will be z raised to 4 by 4 factorial, and the term goes on. Okay. So, when we check it out, this is nothing but cos z. So, now we got an important analogy which says that d by dz of sine z is equal to cos z. So, we again proved another property of the trigonometric functions, which happens to be behaving like the same way we see in the real sense. Okay. Now again let's connect these trigonometric functions with respect to the exponential function. Okay. So we have, let's start with the exponential function we defined. We have e raised to z is equal to summation n is equal to 0 to infinity 1 by n factorial into z raised to n. Okay. That is equal to 1 plus z by 1 factorial plus z square by 2 factorial plus z cube by 3 factorial plus z raised to 4 by 4 factorial plus z raised to 5 by 5 factorial plus etc. Right? Now let's just find out e raised to iz. Okay. When we are finding e raised to iz, we get 1 plus iz divided by 1 factorial. Now the next term is iz the whole square. Iz the whole square is nothing but minus z square divided by 2 factorial. Now plus iz the whole cube, that is nothing but minus I z cube by 3 factorial. The next is iz the whole raised to 4, that is nothing but plus z raised to 4 by 4 factorial. The next term will be plus I z raised to 5 by 5 factorial, then minus etc. It goes on like that. Okay. Now let's just write e raised to minus iz. That is nothing but, when you evaluate, you get 1 minus iz divided by 1 factorial minus z square by 2 factorial plus I z cube by 3 factorial plus I plus not I plus z raised to 4 by 4 factorial minus I z raised to 5 by 5 factorial, and it's going on. Okay. The next thing we are going to do is e raised to iz plus e raised to minus iz. When you check it out, when you add, you get 2 here, these things cancel, these things add up, these things cancel, these things add up, these things cancel, like that. So you get 2 minus 2 into z square by 2 factorial plus 2 into z raised to 4 by 4 factorial minus next will be 2 into z raised to 6 by 6 factorial plus etc. Okay. So that is equal to, when 2 is taken out, you get 1 minus z square by 2 factorial plus z raised to 4 by 4 factorial minus z raised to 6 by 6 factorial plus etc. Okay. That is nothing but 2 into what lies inside the braces is cos z. So now you got a connection between cos z and the exponential function, which is cos z is equal to e raised to iz plus e raised to minus iz divided by 2. So this is another important property which connects both cos z and the exponential function. Okay. Now let's see how we can do the same with respect to sin z. Okay. For that we are going to simply, yes, by intuition we know that we are simply going to subtract Okay, for subtraction I am going to take e raised to iz minus e raised to minus iz. When you calculate, you get it to be 2iz by 1 factorial minus 2iz cube by 3 factorial plus 2I z raised to 5 by 5 factorial minus 2I z raised to 7 by 7 factorial plus etc., which is equal to, I am taking the 2I out, you will get z by 1 factorial minus z cube by 3 factorial plus z raised to 5 by 5 factorial minus z raised to 7 by 7 factorial plus etc., which is equal to 2I into what is in the braces is nothing but sine z. So now you are going to get another important property which says sine z is equal to e raised to iz minus e raised to minus iz divided by 2I. This is also very important property with respect to the relation between both exponential function and the trigonometric functions. Now the next property is something similar to the famous property in the real sense, which is cos square z plus sin square z is equal to 1. This is our claim. So the proof of the claim, we are taking cos square z plus sin square z in the LHS, and cos square z I know it to be e raised to iz plus e raised to minus iz by 2, the whole square here, that is square, plus e raised to iz minus e raised to minus iz divided by 2I, the whole square. Okay, when we are squaring, in the denominator I will be having 4 plus here in the denominator I will be having minus 4. So this will be e raised to iz 2iz minus 2 plus e raised to minus 2iz. Here I have e raised to 2iz minus 2, I am having plus 2 here, minus 2 plus e raised to minus 2iz. So this the minus sign here I am taking here. Okay, so I am having the minus here, and when I am taking the minus inside, I will cancel terms out, and what I get is 4 by 4, which is equal to 1. So thus we proved our claim. So that is another important property which connects sine z and cos z. The sum of the squares of sine z and cos z is equal to 1. Okay. Now think about cos z plus I sin z. Okay, this is equal to e raised to iz plus e raised to minus iz divided by 2 plus I into e raised to iz minus e raised to minus iz divided by 2I. Okay, this I and this I cancels out, and then you get is 2 into e raised to iz divided by 2, which is equal to e raised to iz. This is again a property which we see in real case as the equation called de Moivre's equation. So that property is also satisfied here. Sin z, yet another property of the exponential and the trigonometric functions. Okay. Now, suppose if we just write the equation in real case. Okay. You can call it also the same here. Okay. This is the one among the relationship between exponential function and trigonometric functions. Now, if z is a real number, okay, where theta is purely real, then e raised to I theta will be a real constant, right? Real constant in our complex plane. Okay. Now think about e raised to I theta. We said that e raised to I theta is equal to cos theta plus I sin theta. Okay. Now let's just give a recap of things we have done earlier. If z is equal to x plus iy in C, okay, the corresponding polar coordinates r comma theta, the ordered pair r comma theta is such that it is the same way to represent the point in complex plane, is such that x is equal to r cos theta and y is equal to r sin theta. And also when we learn at first, we know that r sitting here is nothing but the modulus of the modulus means root of x square plus y square, modulus of z, and the theta is the angle between positive real axis and the line segment joining origin 0 and the point z we are talking about. Okay. And this theta is also called as argument of z, argument of z. Okay. So from here I get that for every z belongs to C, we know that z is equal to x plus iy, that is nothing but r cos theta plus r sin theta, I into r sin theta, and that is equal to r into cos theta plus I sin theta. But this is nothing but r into e raised to I theta, right, but r is equal to modulus of z into e raised to I theta. So this is something which we are getting to be an important property of complex number, that is z, any complex number. For every complex number z in C, z is equal to modulus of z into e raised to I theta. Yet another good property of complex numbers connecting to exponential function. Okay. We have earlier obtained that e raised to x into e raised to iy can be written as e raised to x plus iy. Okay. So think about modulus of e raised to z. This we have we have proved. Modulus of e raised to z is equal to e raised to x plus iy, which is equal to modulus of e raised to x into, we can write like this, and the property of modulus function which says that modulus of z1 into z2 is equal to modulus of z1 into modulus of z2. So, here we have modulus of e raised to x into modulus of e raised to iy. Okay. Now, you are going to think about modulus of e raised to iy. Okay. This is equal to modulus of the De Moivre's equation cos y plus I into sin y, which is nothing but root of cos square y plus sin square y. We proved that that is equal to 1. So, that is equal to root of 1, which is equal to 1. So, we just proved that this is equal to that is equal to 1, okay, and this is equal to modulus of e raised to x into 1, okay, but x is a real quantity. So, modulus of e raised to x is nothing but e raised to x itself, okay, and x is what is x? It is the real part of z. So, this is equal to e raised to real part of z. So, what did we obtain now? We obtained yet another nice property which says that modulus of e raised to z is equal to e raised to real part of z. Which is another important property of exponential function. Okay. Now, let us see a simple more conviction. E raised to z is equal to e raised to x plus iy, which is equal to e raised to x into e raised to iy, right. This is equal to r into e raised to iy. Suppose I am saying here r is equal to e raised to x, definitely, okay. So, this means that the r we mentioned earlier is the same here, okay, this r, okay, and we had a theta there which was called the argument. So, here what we are getting is argument of the complex number e raised to z is equal to y, right. What is y? Y is nothing but the imaginary part of z. So, we are getting important results here. Argument of e raised to z is equal to imaginary part of z as well as modulus of e raised to z is equal to e raised to the real part of z. So, these are both are important concepts to think over. Now, we are thinking about the property of periodicity of e raised to z. But note that the periodicity of the real function e raised to x is never mentioned before, and it is not at all presented by the function e raised to x. And this is the main difference between the real exponential function and complex exponential function, which says that the complex exponential function is periodic. So, first of all, for those who are unfamiliar with periodicity, a function f is periodic with period C if f of z plus C is equal to f of z for every z belongs to C. If this property is satisfied, we say that the function is periodic. So, we are going to check whether e raised to z is periodic, right. So, what we are going to do is, we are assuming e raised to z is periodic, and say C is the period of e raised to z, and we are going to find this C, find how this C looks like. Okay. Since C is the period, here we have f of z is equal to e raised to z and C is the period, right. So, f of z plus C is equal to f of z for every z belongs to C. So, that will imply e raised to z plus C is equal to e raised to z for every z belongs to C, right. So, that will mean this is equal to e raised to z into e raised to C, which is equal to e raised to z for every z belongs to C, multiply with e raised to minus z, you get this to be e raised to 0 into e raised to C equal to e raised to 0. E raised to 0 is 1, and that will imply e raised to C is equal to 1. If e raised to C is equal to 1, we have modulus of e raised to C is equal to 1. But modulus of e raised to C is e raised to the real part of C, right. So, we got this to be 1, right. So, real part of C means it is a real number, right. So, e raised to a real number is equal to 1. That we know the real number should be 0, right. So, we got that the period C is purely imaginary, since real part of C is equal to 0. Now, let's see what the imaginary part looks like. Okay. So, definitely C is equal to some I theta, where theta belongs to the real number. Now, 1 is equal to e raised to C, we found it out, and C is of the form I theta, and e raised to I theta is equal to cos theta plus I sin theta, right. Theta is real, theta is a real number. So, we can equate both sides. Cos theta will be equated to 1, sin theta will be equated to 0, right. Cos theta is equal to 1 and sin theta is equal to 0. This simultaneously happens for theta is equal to multiples of 2 pi, where n belongs to z, right. So, that will mean that C is equal to I theta will imply I into 2 pi n, where n is a set of integers. Okay. So, now we got an important information which says period of e raised to z is the integral multiples of of 2 pi I. This is a very important property of exponential function. Since this property is not satisfied by the real exponential function, it is the property or complex exponential function solely satisfy. And just to understand how the periodicity works, I am just drawing a lame diagram. Okay, this is a line. My God, this is a line. Okay, and I am having pi here, minus pi here, and 3 pi here, minus 3 pi here, and then you have my 5 pi here, and minus 5 pi here. Okay, and if we are drawing lines like this, horizontal lines, okay, lines like this, parallel horizontal lines, and each having 2 pi distance between. Okay, so what we are saying that in these horizontal strips, when we are mapping the function to the range, the exponential function will behave the same way in each of the horizontal strips. So that is how we are ending up the session, and the property we said in the end, that is the function e raised to z is a periodic function with a period to be 2 pi n, where n belongs to z, is the most important property of e raised to z. So we are concluding. Thank you.